Okay, anything? Okay, the theme continues to be mixtures of acids and bases. Um, and we were talking about this little problem on Wednesday, um, where I've got a mixture of essentially a weak base and a strong acid. Um, it doesn't really matter particularly whether they're weak or strong for what happened next, except you would not end up with a buffer if they were both strong. But again, the issue is that all of my acids and bases are in water. And so I always have other reactions going on, right? There's the Kas of the acids, the Kbs of the bases, and of course, there's always good old Kw just because water likes to react with itself. And so my general scheme for all of these things, right, is if you have multiple acids and bases, make a list of the acids, make a list of the bases, and make them each react with all of the other matching compounds. So if you have 2 acids and 2 bases, you end up with 4 reactions. If you have 5 acids and 5 bases, you end up with 25 reactions. All right. In the end, most of those reactions usually don't end up being important. All right. But I don't have to decide any of that up front if I don't want to. Right. Because I just let the K decide who goes first. Right. And they sort of sort themselves out. It is worth pointing out that go first is really a calculation time frame. It's not a laboratory time frame, right? These 4 reactions are happening simultaneously all the time, right? And I'm talking about equilibrium here, not kinetics, right? So for all I know, the least important reaction is the fastest, right? But the thing about equilibria, they don't stop reacting. So even if the Kw reaction is so freaking fast that it reaches equilibrium first, right? If it's not that important from an equilibrium standpoint, it's constantly going back and forth, and the other reaction starts stealing from it, if you will. And so my calculation time frame is really based on who ends up being most important long term, right? And the bigger K is the one that ends up dominating, right? They're all going to get to equilibrium. I don't know when any of them get to equilibrium, but once they're all at equilibrium, the changes I see are dominated by the biggest Ks. And so when I say biggest K first, I'm really referring to my calculation, not anything real that's going on in the beaker. And as we saw, I've got 2 essentially infinite or nearly infinite Ks on my list. The HCl Ka, right, by definition for a strong acid, is huge or nearly infinite, or as I prefer to think of it, frickin' big, right? Only because I need to decide on different degrees of nearly infinite. Because when I calculated the K neutralization for that top reaction, it's actually 2 billion times bigger than the Ka of HCl, right? They're both friggin' big, right? They're both going to go to completion, but even in the case of frickin' big, I still solve them in order of biggest to smallest. And what we saw happens here when I do the first one, because there's less HCl, right, it's the limiting reagent. I run out of HCl in the first reaction, which means any later reactions that require HCl can't really happen, right? Which is why I ended up skipping over the HCl reaction, even though it has a nearly infinite K. And even though it's technically happening, I've already essentially wrapped up the HCl situation. There simply isn't any left when everything gets to equilibrium, right? Which brings me to the really only reaction I kind of sort of care about, right? I mean, I have to care about that neutralization reaction, but it's over and done with in a hurry, right? But because of my weak base equilibrium, this ends up being a buffer. And we were saying towards the end of class, when the sun was shining and the birds were singing and there was love in all of our hearts, right? This ends up being a buffer that was made by the fact that I had a strong acid that neutralized some of my weak base, right? I started with only the ammonia, right? But of course, the product of the neutralization reaction includes the conjugate acid. And so essentially, I made the buffer with the first reaction in my mixture. And so I now have initial quantities of both the base and its conjugate acid, and so it's essentially a buffer. This is kind of the second way you can get a buffer. Sometimes, in some sense, quite by accident, right? Because again, typically, if you're doing this reaction, you're probably trying to do the first reaction. I mean, you could be trying to make a buffer. This is a common way people make buffers. But if I do the first reaction, I get left with a buffer along the way, right? And again, I could just solve that K equation the old-fashioned way because all equilibrium problems still have three parts, right? But if I recognize it's a buffer, I can short circuit my solution with Henderson-Hasselbalch. Right. And again, that is a general issue. You see it in titrations, which we'll talk about next week, right? If you have a weak base or a weak acid and you add another acid or base to it, right? As long as the weak thing is left over, right, you will have a buffer, right? If my amounts were switched, right, same two compounds, starting with ammonia and HCl, but I actually have more of the HCl than the ammonia, then in this case, I don't get a buffer, right? Because buffers really only come from weak acids and weak bases, because the strong acids and strong bases completely dissociate in water, so you always only have the one species, right? A buffer requires that I have both of the conjugates present, and that can only happen if I have a weak acid or a weak base. So in this particular case, where ammonia now became the limiting reactant, after that first reaction, I would only have HCl, right? Which means, you know, it's essentially the reverse of the previous situation, right? Last time I skipped the HCl reaction because I was out of HCl and I did the ammonia reaction. Here, I can do the HCl reaction and there's no need to do the ammonia or the water reaction because they won't change anything. And so in this case, I end up with just essentially a solution of a strong acid. There's technically a little bit of the conjugate here, right? So it's kind of a second acid, right? But it's that K is so small, the only reaction that ends up mattering is the strong acid dissociation of HCl. Right. Yes, no. And as I was saying on, I think both Monday and Wednesday, right? That's why really it's not as scary as it might at first sound when I have mixtures of acids and bases. In this case, I had 2 acids and 2 bases, right? There were technically 4 reactions. In either case, whether the ammonia or the HCl was a limiting reagent, there were only ever 2 of them that mattered, right? And this tends to be true, right? Most K neutralizations are frickin' big or bigger, right? Which means if I mix a whole bunch of acids and a whole bunch of bases together, I've got a whole bunch of frickin' big Ks, which means my acids and bases annihilate each other. And every time I run out of something, I lose a whole bunch of reactions that go with it, right? If this HCl and ammonia was 1 acid and 1 base out of 10, right? Sure, there's 100 reactions, 10 for every acid and 10 for every base, right? But after the first reaction, I'm out of either ammonia or HCl, which means I lose 10 reactions. And if I did the next reaction, I would lose probably 10 more, because every one of those frickin' big reactions eliminates a compound from further consideration, which is why I always say it half kiddingly as a threat that I should give you a problem that has 10 acids and 10 bases. All right. But while it would initially give you 100 reactions to consider, which would be a nuisance because you'd have to decide on what the Ks are, right? In the end, I really would probably end up with only a handful of them that matter, right? And usually at most 1 or possibly 2 equilibria because of all the super freaking big reactions that go on. Right. Yes, no? Okay, as I was saying on Wednesday, right, buffers inherently are mixture problems, right? I only have a buffer if I have essentially 2 acid-base compounds to begin with, right? I either need, as we just had, a weak something and a strong opposite thing, or I need to have, as we had on Wednesday, a weak acid or base with its conjugate acid or base. And of course, there's always water. So even just the formation of a buffer is inherently a multiple acid base reaction, right? But even more than that, the only point to making a buffer is because you're trying to prevent the pH from moving, right? The one property that a buffer has that makes it useful is that resistance to pH changes, which means I really only use buffers when I'm adding even more acid or more base to the situation, as in the problem here, right? I have a solution made of ammonia and ammonium chloride. We saw that before. It was our buffer from Wednesday. And then I added HCl to it. Why? Because I can. Why? Because, right, if it's a buffer, presumably that's what I want it to do, right? Now, in this case, I intentionally added the HCl almost as a test of the buffer. In practice, whatever I'm using it for must have an acid in it, right? And so, right, this is where my emphasis on the calculation time frame versus the laboratory time frame is important, right? If you read the actual problem, right, the last thing I added was the HCl. That is irrelevant to the way I solved the problem, right? Because whatever happened before the HCl was present is irrelevant, right? When I mix the ammonia and the ammonium chloride, it reaches equilibrium and I have a buffer. But again, my buffers aren't static. It's not like anything stopped happening. All of the equilibria in my ammonia and ammonium chloride mixture, right, are constantly going back and forth. And so as soon as I add anything else, right, the equilibria shift in response to whatever I've added to find my new equilibrium position. And so it's not a case of really a sequential mixing, right? I can only solve the equilibrium here once everything's in the beaker, right? And so my calculation time frame is always somewhat different than my actual lab time frame, because my lab time frame is literally governed by a clock. I added this, and then I added this, and then I added this. I don't care about the order of adding them when I'm trying to find the equilibrium, right? It's a K issue. Biggest K goes first, even if it's the last thing you added, right? And so essentially, right, this is, again, just a mixture of acids and bases. And so I want to treat it the same way I treat all of my mixtures of acids and bases, which is essentially, right, to make a list of my acids, a list of my bases, and react them all, right? And so this is really, again, the buffer we had on Wednesday, which is governed by this equilibrium, right? This is essentially the buffer equilibrium, right? There is technically also a horrible KB reaction for the chloride, right? There's, of course, KW, and we talked about how technically, since there was ammonium there, if I'm writing all the reactions, right? But these two are essentially the conjugates. And so if you solve one, you solve them both, right? And so when I add the HCl, technically, right, the HCl can react with any of the bases that are there, which adds the essentially 3 reactions, right? Because originally, after I dissociate my ammonium, dissociate my ammonium chloride, I had 2 acids and 3 bases for a grand total of 6 reactions. When I then throw the HCl in there, there are technically 3 HCl reactions, right? This one ends up being the biggest one because, as we've just seen, the K for this is super freaking big. But there's also technically the HCl plus water reaction, which is just the Ka of HCl. And there's technically another one of those stupid reactions of the HCl with its conjugate, which of course technically has a K of 1, but it doesn't really change anything. Right. The net result is, of all now 9 reactions I could have written, right, the biggest K is the ammonia plus the HCl. And again, my brute force approach always works, right? Every acid, every base, find the K's biggest K first, right? I can simplify that a little bit, because the biggest K is always going to be the biggest Ka acid reacting with the biggest Kb base, right? It becomes a little trickier to rank the rest of them. But of my 9 possible reactions, even without determining all of the Ks, there's no doubt HCl plus ammonia has to be the biggest one, because if I look at the Kas and the Kbs, remember my average run-of-the-mill acid-base reaction is Ka times Kb over Kw, right? So if I have the biggest possible Ka with the biggest possible Kb, I'm going to get the biggest possible K neutralization. And so, you know, just based on what these are, the Kb's over here, this one is approximately 0, right? This is 10 to the minus 10. This is 10 to the minus 14. This one's freaking big, right? So the best acid is HCl, and the best base by itself is ammonia, right? And so even without writing down all 9 reactions and ranking all the Ks, right, the ammonia plus HCl reaction has to go first, right? Where that's helpful is it ends up eliminating a bunch of the other reactions, right? And it turns out, right, of all of my possible reactions, this one would be the biggest, right? This one technically would be second, but again, HCl is the limiting reagent, so it can't happen, right? And so again, I'm going to have a case where actually my second biggest reaction that I could do is my buffer reaction again. Technically, all of the Cl minus reactions aren't even worth considering because the Kb of chloride is essentially 0, right? Because this is the conjugate of HCl. So the Kb of that is good old Kw divided by the Ka of HCl, which is nearly infinite or frickin' big or whatever you want to call it, right? And so the Kb of chloride is essentially 0, right? This is why chloride, right, is a perfect spectator. It is really the same issue with the sodium. I sort of dismissed it on Wednesday because I wasn't ready to talk about it, and I'm still not, although I will be by the end of the day, maybe. But, you know, sodium, which I alleged, and I'm not lying, right, is technically an acid. Specifically, it's the conjugate acid of NaOH, which is a strong base. So if you calculate the Ka of sodium, right, it's Kw over the Kb of NaOH, which again is nearly infinite, which makes it 0. Right. We talked about the fact, I need empty real estate here. I've got none. Look at this. This is where I wish I could use the giant whiteboard that's right behind me, right? This is why, as I mentioned before, and it's a general lab thing, right? Sodium salts are common, not because of the sodium, but because of what the sodium brings to the party. If you're looking for a source of a particular anion, right, it has to come partnered with something. So if you want oxalate, for example, right, your best bet is to go to the shelf and get either sodium oxalate or potassium oxalate. Why? Right? There's 3 good reasons, possibly 4, right? 3 of which we could talk about now. 1, they're cheap, right? Part of the reason they're cheap is sodium, if you think all the way back to Chem 1, right, sodium and potassium, right, are highly soluble, right? They're group 1A, right? And if you're going to make a solution, the one thing you do have to have is something that's soluble. But now you can see another major chemical reason why you use sodium or potassium, right? Those are both technically acids, but they're both the conjugate acid of a strong base. right? And so their Kas are 0. Nitrate, which I said is the similar anion equivalent, again, nitrates tend to be highly soluble, see your solubility rules. This is the conjugate of nitric acid, right? And so it has a Kb that's about 0, right? There's a third reason we'll get to later in the semester, right? Third chemical reason, right? But because of solubility and because they are essentially acid and base neutral, even though they're technically acids and bases, right? That's why you see all these sodium and potassium salts, and chloride is similar, which is why even though technically there's chloride in there from the ammonium chloride, I can throw out the chloride as a spectator because it essentially has a Kb of 0. And so my first big reaction is the super frickin' big one. Right. It is very much like our previous problem, except, right, in the previous problem, I did not start with any of the conjugate. Right, in the previous problem, I only had ammonia and HCl. In this case, I also have ammonium. Right, that doesn't really change anything. It's still a limiting reactant problem. HCl is still the limiting reactant. Right, and so the net effect is that I have less ammonia and more ammonium. It just so happens in this case, I'm starting from a baseline of 1.5 moles of ammonium. Right, and the last problem I started with 0. Right, but the net result is still the same. I now have, right, some ammonia and some ammonium. Those are conjugates, and so it's still a buffer. Right, and because my HCl is all gone, and so is the HCl reaction, the next best reaction, right, is my Kb of ammonia, which is my buffer reaction. Right. And so again, you could solve it the old-fashioned way, right? K equation, plug it in, solve for X, go back to the ice chart, substitute X in, see what you get. Or if I recognize it's a buffer, I can Henderson-Hasselbeck it, right? And I can also use my special little property that for Henderson-Hasselbeck, it doesn't have to be molarity. I can live with moles. And so I did. Right? I mentioned when I first threw that out there that I both hate that little shortcut, but it has one place where it's useful. This is where it's useful. Right? Because I've got a buffer, and again, the whole point in using a buffer is to prevent the pH from changing, which implicitly means it's because there's something else being added, right? And the problem with repeatedly adding something to my buffer is I keep diluting everything. And so if I'm using molarity, I constantly have to recalculate the molarities, right? On the other hand, if I'm using moles, I don't have to worry about dilution. I just adjust the number of moles. And so it's usually easier to solve these buffer problems using the moles instead of the molarity because it saves you the dilution calculation. Right. Even though I still maintain it's a bad habit to get into because generally speaking, moles don't work. Right, but if I solve that, I end up with a pH of 9.25. Right, yes, no. I was going to make this point later, but we could also make it now since it's closer to go back. Right, if you look at, right, that original buffer, right, where I had equal amounts of ammonia and ammonium, right, The pH of the buffer was 9.26. Right. So essentially what happened here is I added a little bit of HCl. Right. And when these were equal, so if this was 1.5 moles and 1.5 moles, right, I would get a pH of 9.26. Right. And so adding a little bit of acid to my buffer lowered the pH, but very slightly. Right. And so buffers aren't magic, right? They resist changes to pH, but they don't completely prevent them, right? Because as you'll see in a minute, right, I could keep doing this, right? If I add a little more HCl, this goes down and this goes up. And if I keep doing that, eventually this goes to zero. Right? So any buffer can be eventually undone if you add enough acid or enough base to the mixture. Right? But what makes the buffer a buffer is it's harder to do that with the buffer, right, to change the pH than it would be if it wasn't buffered in the first place. Right? And so we will look at that in mere minutes. I do point out the book and the internet, right, sometimes have a bit of a shorthand for doing this, right? What I did, in keeping with my usual program, right, was to list all of my acid-base reactions and go biggest K first. And I essentially ended up with 2 ice charts because there were 2 reactions that mattered, right? Here's my super freaking big neutralization reaction, much as I hate that word, which was then followed by my KB reaction of ammonia, right? So I had multiple acids and bases, no big surprise. I had multiple acid-base reactions as a result. And it turned out 2 of them mattered. Technically 3 of them, right? Because remember, this 14 minus POH is really KW. I didn't really write a whole ice chart and solve a whole ice chart, but in the end, I actually did end up considering 3 of my 4 reactions. Right. Now, I think that's nice and clean, right? Because again, I can do that for every acid-base mixture I want, no matter how many acids and bases. Take every acid, react it with every base, let the case sort them out, keep solving things till things stop changing. The internet, your textbook, all right. Sometimes shorthand this approach for the buffers. I'm not necessarily a big fan of this. Many of you, or at least many of your predecessors, also not a big fan of this because I think it is kind of confusing. But they sometimes set up these buffer problems as double ice charts, which like 5 years ago, the class started calling icicle charts for some reason. So I have amended it to have the equilibrium in the second one be an LE for last equilibrium. The reason it's confusing, I think, at least potentially confusing, is it really has a hidden reaction, right? The first ice chart, because all I really did here was stack my 2 ice charts together. I put my ammonia plus HCl ice chart on top of the KB of ammonia ice chart. And so that first IC is really a separate reaction, which isn't even written. And so again, it's a shorthand. The book uses it, the internet uses it. So I throw it out to you for clarification. All right. There's no reason to do this because it does for me exactly what the two separate ice charts did. But again, it exists as a shortcut where essentially I've taken this ice chart, right, and put it on top of this ice chart. Because that top reaction was super freaking big, right, it's essentially just a limiting reagent problem. And so, you know, while it's potentially confusing because of the hidden reaction, it does illustrate what adding the acid in this case did. It simultaneously decreased the amount of the ammonia and increased the amount of the conjugate of ammonia, ammonium. All right. And if I had added a base instead of an acid, it would in fact do the reverse, right? If I add NaOH to this buffer, it's going to increase the amount of ammonia and decrease the amount of ammonium. All right. Hang in there, Quinn. You will soon find out. Right. So if I decide to add sodium hydroxide instead of HCl, again, sodium hydroxide is what kind of compound? It's a base. And what? It's also ionic, right? I say that because it can simplify your life if you stick to the program that ionic compounds, when dissolved in water, dissociate. Because the sodium really isn't doing anything. It's a spectator, right? It's really just a source of hydroxide, right? And so, again, I would tend to treat this the same way I treat all of my ionic compounds, even though it's a strong base. It makes your life simpler if I'm not tripping over the sodium. Right? But again, because it's a strong base, right, this has that nearly infinite KB again. And so if I do what I did before, and as I maintain I should almost always do, right, if I've got a mixture, list all of the acids and all of the bases. Technically water on both lists. Technically sodium over here, just to aggravate Quinn again. Technically chloride over here. And I've now added hydroxide over here. Right. I now technically have, Lord help us, right, 3 acids and 4 bases, which means there's technically 12 acid-base reactions, right? But for the reasons I mentioned before, right, the Kb of this is approximately 0 because it's the conjugate of HCl. The Ka of this is approximately 0. So I kind of want to ignore both of these. So I'm down to 6. And so again, the first reaction that should happen, I mean, ultimately, maybe I need to rank all 6 of them. But in principle, the first reaction, right, is always the best Ka with the best Kb, right? I really have 2 horrible acids here, right? Ammonium is 10 to the minus 10. Come on, pen, the minus 10. Look, you can, I don't know why. It just doesn't like both lines there. There you go. 20 to the minus 10. But anyway, this, of course, is 10 to the minus 14. Sure, it lets me do it there. This is 10 to the minus 14. This is 10 to the minus 5. And this is freaking big. Right? So the best base is the hydroxide, the sodium hydroxide. The best acid is actually horrible, but it's still the best acid. You can be the best of a bad lot. That's how my mother always thought of me. It's both insulting to me and my siblings, right? And so the reaction that should happen first is the top one here, because it is super freaking big again, right? And so that reaction does essentially the opposite of my HCl reaction, the last problem, right? It decreases the amount of ammonium, the conjugate acid, and it increases the amount of the ammonia, the conjugate base, right? And so again, if I use the shorthand, right, this is really this reaction. If you prefer, and I sometimes do, right, you can do those as two separate ice charts, right? But you can see what it did. It just did exactly the opposite of what my HCl did. I have a little less ammonium, the acid part of the conjugate pair, and I have a little more of the ammonia, the base part of the conjugate pair. And so my pH, instead of going down that little bit, went up a little bit, right? Okay. It's worth pointing out, because I keep saying it's a buffer, it's resisting the changes in pH, right? If I did that exact same thing to unbuffered ammonia, right? Instead of adding 10 milliliters of 1 molar HCl to the buffer, I'm going to add exactly the same amount of HCl to exactly the same amount of ammonia without the ammonium, right? And just for reference, if I have just plain ammonia, right, my starting pH would be 11.72. Right, so this is just ammonia, no HCl. Right, if I then add a little HCl, right, I'm using molarities. I don't know why. I could have used moles, but I use molarities instead. Right. Again, the little bit of HCl decreases the amount of ammonia and increases the amount of ammonium, which actually creates the buffer. Not a very good one, but a buffer nonetheless. And because it's not a very good one, I didn't Henderson-Hasselbeck, right? If I solve for the pH for my new amounts of ammonia and ammonium, I get a pH of 11.43. Right, and so that's essentially my buffer in action, right? When I had both the ammonia and the ammonium, right, that same amount of acid took me from 9.26 to 9.25, right? Without the buffer being present, I went from 11.72 to 11.43, a much, much bigger change in pH. I mean, notice they're both changing, right? You can't help it. If you start adding acid, the pH is going to start dropping, right? But it's going to drop faster if I'm not buffered, right? The question in the chat was, how do I know it's not a very good buffer? The reason I know it's not a very good buffer is because there's very, very little NH4 plus relative to the amount of NH3. To Derek's point, it is diluted because I added right? It was only 1.5 molar when I had no HCl in it. All right. I'm going to stop there so as not to go over. But for Monday, right, what you can see is the buffer does mitigate the changes in pH, but it doesn't stop them. And so it is not usually good enough for reasons related to the question of good buffer, bad buffer, to simply say I have a buffer. And so buffers have what's termed a buffer capacity, which essentially defines how much acid or base they can eat, right? And that will be Monday's exciting calculation. Sprint Synthesis 3 is technically due this week, isn't it? This coming week, Tuesday. It is on the calendar. The Dropbox isn't there yet, but it will be shortly.